Thanks, and good morning. I'm Erik, and I work at Red Hat, where I contribute to the Red Analytics IO upstream open source community. And so, show of hands, how many of you use abstract algebras in your day-to-day work? Two hands, okay. So I'm hoping that by the end of this talk, you'll find out that actually all of you are being too hard on yourselves. We all use algebras every day when we do this kind of work. So in the beginning, there was data. And the data model is very simple. If you had a data set, it lived in one file and on a single machine. And working with this data was also correspondingly pretty easy. If you wanted to sum some numbers in your data set, you just initialize an accumulator and iterate over your numbers and accumulate into your sum, and when you're done, you have the sum of your data. But things didn't stay that simple forever. So in the early 2000s, Google published their two famous papers on Google FS and MapReduce. And in a couple of years, of course, that had evolved into Hadoop and HDFS. And it wasn't too long after that AmpLab and Mate gave us Spark and the RDD compute model that we all know and love. And more recently, of course, they've extended the RDD model with data frames and structured streaming on top of that. So the commodity scale-out revolution left behind a somewhat different world for us. We still have a logical view of a single data set, but under the hood, physically the data is actually residing in multiple partitions which live in different files and quite possibly, of course, on different machines altogether. So in the scale-out world, sum is a little bit different than it was before. You start with an accumulator on a particular partition and iterate the same way. But now you have a partial result, and you're collecting a partial sum, in this case, across all of your partitions, and at the end of that, you have to take those partial results and start merging them together to get your actual final result. So just for fun, let's consider a different kind of operation over our data, in this case, finding our unique elements. Here we also start an accumulator, but it's the empty set. And in a partition, we're just doing set insertion over our elements. And in our case, our partial result is a set of unique elements just for the partition. And so, again, though, we're collecting partial results across partitions. And here we're merging again, but merging is not addition, it's actually set union. Looking at these two examples, a couple patterns start to emerge. In both cases, you're initializing accumulators. For sum, it's 0, and for unique, it's the empty set. But the pattern is that in each case, there's a value that behaves like 0 or an identity element. Likewise, when we're working within a single partition, we're taking results and inserting them into an accumulator. For sum, of course, that's just numeric addition. For unique elements, it's, again, set insertion, but the basic pattern is frequently called update. You'll also see this referred to as reduce, depending on the kind of library you're working with. And lastly, once we've collected partial results, we have to merge them. And so again, for sum, this is just addition, but for unique elements, it's set union. And the pattern is called merge, frequently in libraries. You'll also see this called combine. So, of course, Spark comes prepackaged with a whole zoo of operators that behave like this. We just saw how sum works. It works on numeric data and has a numeric accumulator. Maximum also works on numeric data, and its accumulator is also just a single number. Its 0 is a little funny. It's actually minus infinity. And then update is just, taking maximums with your accumulator, and merging is also maximum. Another one is average, which is a little bit more interesting. It also, of course, just receives numeric data, but its accumulator is a pair of numbers. It's a sum and, of course, a count of elements. And 0 is just a pair of zeros for both of those. Update, you take the sum and add in your data elements, but you just increment the counter. And when you're merging, you're simply doing pairwise addition, of course. And then at the end, for average, you have to do a sort of extra operation called present, where you don't give the user a pair of numbers. You take the sum and divide it by the count, and you give a single number back to the user. So the first big takeaway I want to leave with people today is that if you're filling out these kinds of tables of patterns, you're already most of the way to defining an abstract algebra. Algebras really are just pattern checklists, so you're defining like object sets. And of course in the software world these basically appear as data types. You're defining some operations on those sets, and the operations may have some properties that you have to check off. So if you consider this a DataFrame aggregation where you just have some users with word counts, and say you want to group by users and then take the average word counts. Well, we saw just a minute ago that average is actually fulfilling one of these pattern checklists, and so the implication is that if you guys are doing any of these kinds of aggregations, you're working with algebras. So what kind of an algebra is an aggregation? Well, it comes with a data type. In other words, what data elements it actually expects. There is some kind of type for these accumulators you're using. The accumulator has some special value that behaves like a 0, and it has an update where you insert objects and accumulate them in your accumulator. And at the end, you have to merge partial results with these accumulators. And lastly, you may do a special operation that actually, takes the raw accumulator and presents it to the user in some more presentable form. So I want to talk a little bit about merge. One property that merge must obey is associativity, and all that really means is if you consider merging these left two elements, you get one result, and of course if you merge the right two first, you get the same result. And if you don't have this property, it basically would prevent you from getting a stable result when you're trying to combine the final results of your partitions. And so this is basically a mandatory property for any kind of merge operation. Now out in the wild, most merge operations are also usually commutative. And of course, what that means is that when you're getting partial results coming in off of your partitions, you can just totally reorder them. And of course, this is also a very nice property because it means you can literally take them as they come in any order, merge them, and you have yourself, again, a stable final result to present to the user. And as we've seen, sum, of course, is commutative, as we all learned in school, and likewise, if you change the order of maximum, you get the same result. And for average, these pairs you're adding, also commutative, because of course the pairs you're adding inside are all using commutative addition. So again, pretty much any operator you're going to see prepackaged out of Spark is going to have a commutative merge operation for their algebra. So this is a talk about structure streaming, and structure streaming is a little bit different than just simple data frames. In it, you of course have data coming in at different times, and logically you have an ever-growing data frame, and then paired with that the result of, say, an aggregation over that theoretically unbounded data stream. So here we can see we have some new data coming in, and logically it's been appended to the previous data, but secretly it's discarded the data that came in before, and the aggregation is reflecting the result over all the data it's seen so far. And this just continues. You keep seeing new data come in, and logically the data set never stops growing, but physically it stays small. You're just looking at local data, and the aggregation itself is basically a bounded kind of data set. So how is all that possible? If you consider one of these little batches, you might do a group by if you've requested some kind of grouping. And then you use this update operator, which we just talked about, to take these group-wise results and reduce them into some aggregate, in this case just summing. And then you take those partial results and you merge them in with your accumulating aggregation that you're actually going to return as the result. So as we just saw, these update and merge are part of a kind of algebra, and so in a very real sense, structured streaming is powered by algebras. Now, to date, I've been talking only about examples of these aggregations that come packaged in Spark, but the real story I wanted to get to today was that a lot of more interesting kinds of business logic actually can fit this same algebraic pattern. So if you have some idea for a kind of business logic you'd like to run, if you can express it in a form that checks off all of these properties of an aggregating algebra, then you get to write that as a structured streaming query and integrate it fully with all of Spark's structured streaming features. So what's an example of that? Suppose you want to do aggregation and extract quantiles from your data. So you have some numeric data, and you like to ask questions like, what's the median of my data, or what's the 90th percentile? How could you do that as an aggregating query? Well, I happen to know about a particular kind of sketch. It's called a t-digest, and t-digest basically provides you an estimate of the cumulative distribution of your data. Now, what can you do with that? If you want, say, the 90th percentile, you turn that into this Q value, 0.9, and you go and find the value of X that corresponds to that particular quantile. And that value of X is the 90th percentile for your data. T-digests themselves are very interesting. I don't have any time to really talk about them today, but if you're interested in learning about how those work, that link down at the bottom left goes to a previous Spark Summit talk I gave that is all about t-digests and how they operate. So, is t-digest an algebra? Well, we can define a data type. It's basically numbers of any kind. The accumulator type is this t-digest sketch that I just discussed. There is a very well-defined idea of an empty t-digest, so that can be my zero value. Again, it's also very well defined how to insert a number into one of these sketches, and it's also possible, if you're careful, to define how to merge two t-digests and get a stable result. And lastly, if you want to present the user with an actual quantile, you can just take one of these objects and say, give me the inverse CDF of my quantile, and that gives you the actual percentile that the user would like. So yes, t-digests are an algebra, and that means that I can write a structured streaming aggregating query on it. So Spark provides mechanisms for doing this. You can define what's called a user-defined aggregator. And here you can see that I've got a little function which allows me to declare one of these things to sketch a CDF. And then I'm going to do a little trick, which is that I know that once you have one of these things, you can take any kind of quantile you want off of it. And so I'm going to declare a couple of user-defined functions which expect one of these t-digest results and just give you the quantile back. So I can compute a t-digest once and give the user as many quantiles as they desire, and not have to do one for each. And if you are interested in learning more about how to write things like user-defined aggregators, my friend Will Benton and I are giving a talk about Spark for library developers later this afternoon, and that link just goes to the schedule entry for that. So what does this look like in a structured streaming query? If you look at these emphasized code here, you can see that I'm grouping by just time windows using Spark's predefined facilities for that. And I can just now take my user-defined aggregator and drop it straight into the aggregator operation for the streaming. And then after I'm done with that, I'm using a little select to invoke my special user-defined functions that give me the 50th and 90th percentile. And you can see at the bottom that when I ran this in a notebook, it gave me the median and a 90th percentile for a stream of word counts. So this is a good example of once you get it into this kind of form, you can just integrate automatically with essentially every streaming feature that Spark gives you. So it's very powerful. And if you're interested in actually doing this kind of percentile extraction, I've actually written a library which allows you to do this, and it supports PySpark and the JVM Spark, so that link takes you to just to the GitHub repo. So I'll just consider a second kind of application. Suppose that you're interested in tracking the most frequent items in some stream. Here we're just talking about some, say, social media hashtags. And what we'd like coming out is a little table with the most common tags and some frequency. So is there a way we can actually create a structured streaming aggregation for that kind of business logic? There is. It's called typically in the literature a heavy hitter sketch. And inside of a heavy hitter sketch, there are actually two data structures. One is what's called a count-min sketch. And some of you may know that Spark actually comes with a count-min sketch, which you can use. And what a count-min sketch does is it provides estimates of frequencies of objects. And it does this in a scalable way that takes a constant amount of space regardless of how much data you actually throw at it. And what you have to pay is that it's an estimate of the frequency, and it's not the exact frequency. Now the second data structure is just a classic heap for storing elements in a sorted order. Now you can see that I've deliberately drawn these as sort of cartoon black boxes because again, I'm not really here to talk about like the details of how certain data sketches work. But I will sort of discuss the overall logic. So you have an item coming in our case it would be some kind of social media hashtag, and you insert it into one of these count-min sketches to update all of its frequency estimates. Once you've updated the estimates, you then query back into it to get the estimated frequency for this object that's come in. And you take that pair, that's the frequency with its corresponding object, and you insert it into the heap. So you're basically storing the top frequencies ordered using just the heap, which of course does these things in log time, very efficient. And when you're done, you can just query the heap object to get the top k objects that you actually estimated frequencies for. And as I mentioned, I don't really have time to discuss the details of how these, but if you want to see the original paper where they published the count-min sketch, there actually is a section towards the bottom where they say, oh, you can pair this with a heap to get heavy hitters. And that link there will take you to that paper. So it's time to play my new favorite game, Is Heavy Hitter in Algebra? Well, the data type is really anything that you can hash or insert into a heap, which is really literally any kind of data at all. So there's essentially no restriction on the data type that I can operate on here. For an accumulator, it's these two data structures I just described, a count-min sketch paired with a heap, so I can check that box off. There's a 0 because basically it is well defined that you can have an empty sketch for the count-min and A heap, of course, can always start out as empty, so I have myself a well-defined 0. For update, it works kind of like how I described. You insert a value into your count min, and then query it back to get its frequency and insert that pair into your heap. So update is satisfied. And it is also basically very straightforward to take 2 count mins, merge them together. And to do the heap, it's a little bit more involved, but you basically first merge the count mins to get updated frequencies combined from 2 partitions, and then run through all the values in the 2 heaps and query against them and reinsert into a third. So that gives you essentially a merge for a heavy hitter sketch. And lastly, to present to the user, you can simply present those top K values. So I can click off the present structure as well. So yes, heavy hitter is also an algebra. And as with doing percentiles, I can create for myself a special aggregator. In this case, I just called it top K ag, and store that in a value. And I can group by, again, time windows and just drop this top 3 aggregation straight into the Spark's streaming query aggregator. And at the end, you can see that it automatically spits out a little table, and the table I just expressed as a list of ordered pairs. So you're getting basically the top 3 social media tags in a stream at any given point. So to review, we talked about what computing looks like on scale-out data models, and we discussed a few patterns that we could find in those operations. And we built those patterns out into the idea of an algebra, and we showed how structured streaming in Spark is, powered by these algebras under the hood. And then we showed that you can actually take interesting new business logic cases and map them into the same kind of algebra. And then we showed what that actually looks like to invoke these new algebras inside of a Spark structured streaming. So I hope that this talk has showed you that instead of making things like difficult and weird, algebras are actually a great tool to make it easy for mapping your own custom business logic into the space where you can leverage the full power of structured streaming queries. And thanks again for coming. Are there any questions?
Thank you. We have time. I know why my father always told, learn algebra, it'll come handy in life. Now I can see why. Yeah, we have a question over there.
Hey, great talk. So when you take this idea of an algebra aggregator further, have you investigated other abstract algebraic operations like quotients or pullbacks or pushouts and what those mean in this context?
I personally haven't done that, no. But if you want to reach out to me offline, either today or on my social media, we could talk about that. I'd probably be an opportunity for me to expand, like you say, deeper into the query space.
Any other question?
So when you did the window function, I wanted to ask if you have any opportunity to do it by a monthly calendar, the window function.
I did not. I just pretty much, I haven't used it much past the actual time windowing, examples that I showed here. I did briefly experiment with using the over keyword, so to do more sort of generalized windows. I decided not to put it in the talk because I felt like it was a little harder to explain what the results actually were. But again, it pretty much works because it's sort of the feature is orthogonal. The aggregator will pretty much drop in with any windowing logic that Spark can provide or that you can define.
But monthly aggregation calendaring, not by days, it's a bit different. because the slide is, let's say, April and March. You want it to keep moving, and you want to see the last month, so it's
Yes.
a bit difference.
Well, you know that the,
Yeah.
let's see if I can find them. I did use the third parameter, like you know that the window
Yeah.
function can take the third parameter for like, you know, that kind of sliding. I didn't put it in here just because
Yeah.
I actually made it hard to fit into my slide, but I did drop that in and it will give results, you know, the same way. So it'll have this, that sliding window logic will come out of your streaming.
Okay. And can I have another question? In the algebra aggregation, do you have the opportunity to do like pivoting or unpivoting?
I didn't catch that last bit.
Pivot. To do pivot if you have like streaming data and you want to like doing instead of aggregation to do like pivot to the table from.
Oh, pivot.
Yeah.
I have not actually pivoted with this. I assume it would work, but of course that's a more expensive operation. Yeah, I mean, I would claim that it should work because again the feature's orthogonal, but I would, you know, I've never tried it, so.
Okay, thank you.
Yeah, I mean, the pivot was introduced in 2.3 or 2.2 in the DataFrame. So I think since this is the DataFrame API, if you actually did the pivot, it might work. I don't know how it actually would scale with his T-Digest, but you might want to try it and let us know if it doesn't. You had
I just had a quick question whether this reminded me a bit of the monoid data structure. Have you sort of looked at, has that link occurred to you? Or
Yes,
is that?
I have been required by my group ever to say the word monoid, but there is absolutely a monoid hiding in here. I mean, the zero in the merge and its properties, you know, that's the monoid. In fact, I wrote a blog post which I didn't bother linking to, but like, you know, I claim that aggregators are basically what I call a left folding monoid or a reducing monoid. Because when I start using the word, people like sort of shut down and, you know, don't. I wanted to make it accessible, and so I didn't want to use any you know, actual algebra terminology. That was my goal. So.
We take a last question.
So I have one question about the 92 slide, the one where we have the heavy hitcher sketch.
Uh-huh.
So the moment we have the insert in the heap, is it inside the scope of the worker in Spark, or is a large, the heap here is a scope in the workers? It's like we should see it in some insert in heap inside workers, or it's just a heap in a single machine?
It is like a heap in the sense of the sorting heap. So it's unfortunately, heap is a terrible name because it's overloaded in so many ways, but it's a particular very old data structure for inserting objects and keeping them in sorted order for logarithmic time. And so it's just, you know, there's actually a class, I defined a class, and inside is one of these heaps and also a count-min stitch, so it's basically packaged black box wise. But I can tell you more offline though about how to.
Okay, thank you.
Were you asking whether the data structure is actually kept on each and every executor, whether the heap is done in parallel or just on the driver?
Oh yeah, it's.
You mean the off heap, JVM's off heap, or on the executor? Okay. Well, he was asking whether this all is done off heap JVM of heap on the executor or driver?
Oh, yeah, different kind of heap, yeah. Yeah, it's confusing.
Okay, give a big hand to Erik. Thanks all for coming.